Comparison between Fresnel diffraction and Fraunhofer diffraction. Fresnel's diffraction or Fresnel diffraction and Fraunhofer diffraction. Fraunhofer diffraction. Comparison between Fresnel diffraction and Fraunhofer diffraction. So here he is Augustin Fresnel, and right hand side name of the scientist is Joseph van Fraunhofer. Joseph van Fraunhofer. Augustin Fresnel and Joseph van Fraunhofer. For Fresnel diffraction, source of light will be at finite distance. Source of light and screen, that is the observation point at which diffraction pattern will be formed, will be at finite distance. Source of light and screen, that is observation point, are at finite distance from the aperture or the obstacle. From the slit, that is the aperture or the obstacle. For Fraunhofer diffraction, source of light and the screen, that is the observation point, are at infinite distances from the slit under bracket aperture, from the slit, that is the aperture bracket closed, or the obstacle. For Fresnel diffraction, source of light and the screen are at finite distances from the slit or obstacle, and the right hand side for Fraunhofer diffraction, source of light and screen will be at infinite distances from the slit and the obstacle. So here source of light and screen will be at infinite distance from the slit, that is the aperture or the obstacle. In the diagram for Fresnel diffraction, we can consider an aperture AB. This is the aperture or slit AB or narrow aperture AB, and a source of light or point source of light is at finite distance from the aperture AB, and screen is also placed at finite distance from the aperture AB. And rays from the point sources are diverging towards the aperture AB. Rays are diverging towards the aperture AB or towards the slit AB, and diffraction occurs at the sharp corners, that is at the sharp corners A and B of the aperture. And these are the diffracted ray, that means light waves bent at the sharp corners of the aperture AB. And these are the diffracted rays or secondary wavelets which are originating from the sharp corners of the aperture AB. This is the diffracted ray or secondary wavelets, and they will be converging towards the screen, and these are the diffracted rays or secondary wavelets, and they are converging towards the screen at the point P. A number of secondary wavelets will superimpose at the point P on the screen. Due to superposition of secondary wavelets originated from the aperture AB, diffraction pattern is formed on the screen, and we have shown the variation of intensity of different fringes or diffraction pattern with respect to phase difference, and that is plotted and shown in the figure. And AB is the aperture or narrow aperture or narrow slit, whose width is comparable to wavelength of light, and in this case the source S is at finite distance from the aperture AB or from the slit AB. Similarly, screen is also at finite distance from the aperture AB. For Fraunhofer diffraction, we can consider the diagram in which AB is the slit or aperture. AB is the narrow slit or aperture whose width is comparable to wavelength of light. Screen is placed at a certain distance, and a point source S is also placed at the certain distance. But for Fraunhofer diffraction, source of light should be at infinite distance from the aperture AB. In the diagram, S is the source of light or point source of light, and a convex lens L1 is placed in front of the source of light. That is, the convex lens L1 is placed between the point source of light S and the aperture AB, such that the source of light S is at the first principal focus of the lens L1, such that parallel rays are originating from the lens L1, and parallel rays will appear to come from infinite distance with respect to the aperture AB. And after diffraction, and also another convex lens L2 is placed in front of the aperture AB. L2 is the convex lens which is placed in front of the aperture AB. Diffracted rays are diffracted along this direction, and after refraction through the lens L2, the rays will converge at the point P on the screen. These are the converging rays coming from the lens L2, and they will superimpose this diffracted rays which are refracted through the lens L2 will superimpose at the point P on the screen, and diffraction pattern will be obtained on the screen due to superposition of the secondary wavelets coming from the aperture AB. Now we can show the diffracted rays or secondary wavelets. These are the diffracted rays or the secondary wavelets coming from the aperture AB, and these diffracted rays will be refracted through the convex lens L2 and superimpose at the point P on the screen, and diffraction pattern will be obtained, and we can draw the graph of variation of intensity of diffraction pattern with respect to phase difference. Now we can show zero intensity minimum on the diffraction pattern graph. This is the zero intensity minimum, and for Fraunhofer diffraction we get zero intensity minimum. That means the graph will touch the phase difference axis, and these are the zero intensity minimum. Similarly, we can show the nature of minimum for Fresnel diffraction. For Fresnel diffraction, there will be non-zero intensity minimum. This is non-zero intensity minimum, and there is certain distance between the graph and the phase difference axis. For Fraunhofer diffraction, parallel rays will appear to originate from the convex lens L1. That means source of light is at infinite distance. Source of light will appear to be situated at infinite distance from the aperture AB. That means parallel rays are coming from the lens L1, means these rays are coming from infinite distance. That means for Fraunhofer diffraction of light, source of light will appear to be situated at infinite distance. Similarly, the screen will appear to be situated at infinite distance due to presence of the convex lens L1 and L2. L1 and L2. For Fresnel diffraction pattern, on the left hand side for Fresnel diffraction pattern, incident wavefront on the aperture is either spherical or cylindrical. So S is the source of light and AB is the aperture. AB is the aperture, and rays are diverging from the source of light, and rays are diverging towards the aperture AB from the source of light. So, in this case, as the rays are diverging towards the aperture AB, as the rays are diverging from the point source A's, that's why the incident wavefront will be spherical. The incident wavefront will be spherical with respect to the diverging rays from the point source A's. This is the spherical wavefront coming from the point source A's, and this spherical wavefront will be incident on the slit or narrow slit or aperture AB. This is the incident spherical wavefront coming from the source of light, and it will be incident on the aperture AB. Similarly, diffracted rays are converging towards a point P on the screen, and the diffracted wavefront it will be spherical again because the diffracted rays are converging. This is diffracted rays are converging in, and we get diffracted spherical wavefront. Hence, the diffracted wavefront. Hence, the diffracted wavefront from the aperture AB is also spherical or cylindrical. Diffracted wavefront from the aperture is also either spherical or cylindrical or cylindrical. Diffracted wavefront from the aperture is also either spherical or cylindrical. For Fraunhofer diffraction on the right hand side, the incident wavefront on the aperture or the narrow slit is plane wavefront. Incident uh, wavefront on the aperture will be a plane wavefront. Therefore, incident wavefront on the aperture will be a plane wavefront. Now we can show the incident plane wavefront with respect to the parallel rays coming from the convex lens L1. Here, this is the incident plane wavefront. This is the incident plane wavefront or plane wavefront which will be incident on the aperture AB, and this incident wavefront is considered with respect to the parallel rays coming from the convex lens L1. Similarly, these are the diffracted rays from the sharp corners of the aperture AB, and we can consider again diffracted plane wavefront with respect to the parallel diffracted rays from the aperture AB. This is the diffracted plane wavefront. So for Fraunhofer diffraction pattern or Fraunhofer diffraction number 4 point will be what? The diffracted wavefront, the diffracted wavefront originated from the aperture is also a plane wavefront, is also a plane wavefront. The diffracted wavefront from the aperture is a plane wavefront, is a plane wavefront. Number 5, comparison between Fresnel diffraction and Fraunhofer diffraction. On the left hand side, no lenses are required to study the diffraction pattern. No lenses are required to study the diffraction pattern. And on the right hand side, what we can write, two convex lenses are required to form diffraction pattern for Fraunhofer diffraction. Two convex lenses are required to study the diffraction pattern or Fraunhofer diffraction pattern. Two convex lenses are required to study Fraunhofer diffraction pattern. Now we can draw Fresnel diffraction pattern intensity graph, and also right hand side we can draw Fraunhofer diffraction pattern intensity graph. Here Fresnel diffraction intensity pattern on the left hand side, and on the right hand side we shall draw Fraunhofer's diffraction intensity pattern. Fraunhofer diffraction intensity pattern. On the left hand side we can plot the variation of intensity of diffracted rays with respect to phase difference. Here, this is the phase difference axis, horizontal axis is the phase difference axis, and we can denote the variation of intensity of resultant diffracted wave. And here again on the right hand side we can denote the variation of intensity of diffracted rays with the phase difference. Now for Fraunhofer diffraction pattern we can show non-zero intensity minimum. This is intensity non-zero intensity minimum or minima. So that means the intensity, this is the intensity or maximum intensity or intensity of central maximum. On the right hand side again, this is the maximum intensity or maxima, or and we can also show zero intensity minima, which indicates that the intensity of secondary minimum is 0. Intensity of secondary minimum is 0 for Fraunhofer diffraction, but for Fresnel diffraction, intensity of secondary minima is not 0. Number 7, comparison between Fresnel diffraction and Fraunhofer diffraction. For Fresnel diffraction, the maxima and minima are not well defined. Maxima and minima are not well defined. That means bright fringes and dark fringes are not well defined. But for Fraunhofer diffraction pattern, the maxima and the minima are well defined. Well defined.